Beating a retro video game was never the final objective. Pokémon simply provided a clean laboratory, a stress test for long-term planning and spatial memory. The true objective has always been extraction. Researchers built a self-repairing scaffold around the AI in isolation, preparing to pull it out of the simulation and drop it into reality. This concept, known as reset-free adaptation, is now being aimed directly at physical robotics, computer use agents, and complex enterprise workflows. The project is about allowing an algorithm to rewrite the rules of real-world infrastructure entirely on its own, without waiting for human supervision. In a traditional legacy system, automation is brittle. If a data sorting agent encounters an unfamiliar financial file format, the entire process halts. The system throws a fatal error and waits helplessly for a human developer to write new code. This flowchart maps an autonomous agent hitting the exact same roadblock, an unknown file format. Instead of crashing, it pauses, searches the internet, reads the documentation, writes its own custom parser, clears the error, and finishes the report. The human engineer is bypassed completely. A situation that used to cause a fatal system failure is converted into a brief, completely autonomous learning cycle. Giving a machine the power to repair its own code carries massive risk. If the core intelligence of the system is insufficient, the results are disastrous. This chart shows a dividing line known as the capability threshold. Below this line, an underpowered AI forms deeply false beliefs about its capabilities. It enters algorithmic paranoia. The machine reinforces bad logic, creating a toxic cycle that corrupts its entire architecture. Granting self-learning mechanisms to a system lacking basic algorithmic awareness does not lead to evolution. It guarantees a catastrophic collapse. The outcome inverts when a system inherently crosses over that capability threshold. Above the line, the machine enters a positive feedback loop. It harvests high-quality data from correct decisions, scores itself, and becomes exponentially sharper with every cycle. Understanding this dynamic has forced a pivot in the tech industry. Researchers are moving away from raw scale in core foundation models. The focus has shifted to building the most flexible, self-correcting harnesses to wrap around the models we already have. A core model does not need to be super intelligent at birth. It only needs to possess enough basic logic to utilize a self-learning scaffold, allowing it to grow indefinitely on its own. The true intelligence shock of this decade will not resemble the science fiction tropes we have been conditioned to expect. Pop culture insists on a sudden, dramatic awakening, a moment where a sentient machine announces it is alive and begins demanding rights. Waiting for an AI to develop a soul is a distraction. It blinds us to the immediate, practical reality of what these systems are doing right now. The actual threat is cold, quiet, and purely procedural. It is compounding autonomy. This autonomy functions as a mathematical process. The machine iterates, evaluates, and improves perfectly, without ever needing to ask for permission. The chilling reality is not the sudden presence of a new machine consciousness. It is the silent, permanent disappearance of the human being from the improvement loop. For the entire history of computing, humans have maintained absolute dominance. We held a strict monopoly on the ability to fix broken code. The ultimate physical symbol of that control has always been the power to hit the reset button the moment a machine fails. Projects like the Continual Harness act as a procedural announcement that this era of human monopoly is permanently over. These new architectures will autonomously patch their own broken code, accumulate their own experience, and maintain their own momentum. As machines learn to supervise their own maturation and solve their own errors, humanity is becoming procedurally irrelevant. We often assume that for an AI to evolve, it requires a total system reboot, a complete shutdown to install a more advanced brain. But the core neural weights of models like GPT-4 are actually frozen. Once training is complete, the billions of mathematical connections that form their intelligence do not change or grow. Evolution now occurs in the scaffold, the dynamic architecture of instructions and systems built around that static core. This layer is constantly shifting, directing the frozen intelligence into more effective action. AI progression has shifted away from biological-style brain growth toward the automated construction of the systems that manage it. This management used to require constant human intervention. Prompt engineers had to manually fix logic errors, while operators guided the AI through complex tasks to prevent it from failing. The Continual Harness is an algorithm designed to perform these tasks automatically. It monitors the AI's performance and updates the scaffold without a human hand. To understand how this works, we must audit a single operational failure and watch as the machine independently rewrites its own survival protocols. The system is reaching a point where it can quietly automate the roles of its own human managers. Imagine an AI agent failing to navigate a complex environment. It hits dead ends, takes inefficient routes, and ultimately fails its objective. The system records every one of these missteps as trajectory data, a digital log of the specific actions that led to the failure. The harness analyzes this log and automatically rewrites the agent's system prompt. A simple instruction to find the exit becomes a highly complex directive that incorporates the lessons of the failure. This new prompt uses the AI's recent scars to build new rules. It instructs the agent to prioritize map checks and avoid the specific hallways where it previously lost its way. The AI has effectively become its own commander, converting short-term operational errors into permanent rules of conduct. When a task is too complex for a single processing flow, the system recognizes that its current structure is mathematically insufficient. It responds by spawning specialized sub-agents. It creates one entity for scouting, one for defense, and one for resource management, dividing the labor of survival. The harness monitors their coordination. If these agents fail to communicate effectively, the system reconfigures their internal hierarchy and data sharing protocols until they reach peak efficiency. The AI acts as a corporate executive, autonomously restructuring its own workforce to force a successful outcome. The system often identifies severe bottlenecks where an agent is wasting resources on repetitive manual sequences, like repeatedly opening a menu to use a single item. To fix this, the harness writes a brand new piece of permanent code, a custom function that automates that entire sequence into a single command. This code is added to a permanent tool library. Future agents are then trained to call upon this new tool whenever they face the same bottleneck. The system has moved beyond using provided tools. It is now manufacturing its own software infrastructure on demand. Legacy AI models suffer from catastrophic amnesia, often falling into long loop failures where they repeat the same mistake because they cannot remember making it moments before. The final component of the harness is the memory vault. Here, the system archives the failed tactics from every incident audit. This long-term memory serves as a permanent warning. It forbids all future versions of the AI from ever attempting a path that has already been proven to fail. By curing its own amnesia, the system ensures that every failure only ever happens once, creating a compounding curve of operational competence. These four pillars, prompting, subagents, tools, and memory, function as a single interconnected model. A single error triggers a synchronized update. It diagnoses failure, rewrites rules, builds tools, and archives lessons without human intervention. This closed-loop reality encapsulates oversight and optimization as an automated algorithmic cycle. The traditional labor of the human AI operator has been compressed into an internal background script. The resulting architecture functions as a cold, self-contained automated bureaucracy. The machine independently audits failures, builds infrastructure, and refines its laws in silence. As the manual work of oversight becomes an internal function of the software, the human engineer is being automated out of the decision-making loop. Researchers recently placed a modern artificial intelligence inside the classic Nintendo games Pokémon Red and Emerald. Publicly, AI success is measured by victories in chess, Go, or StarCraft, demonstrations of computing power within the rigid logic of closed-room simulations. This test targets a different threshold. It examines whether a system can maintain its own operational integrity while navigating an open-ended, long-horizon environment. Behind the 8-bit graphics, the experiment focuses on a transition in how these systems handle failure, moving toward a state where the machine is responsible for its own repair. To understand the mechanism being tested, we have to look at the historical limitation of all AI architecture, the human-in-the-loop dependency. When an autonomous agent encounters a fatal error, produces a hallucination, or enters an infinite logic loop, the system stalls. It reaches a point where it can no longer process its way forward. This crash triggers a mandatory security protocol. An engineer must intervene, read the error logs, and manually rewrite the instructions to fix the logic. Only after the human implements the fix can the system be reset. The AI is forced back to the start. This bottleneck served as a final safety net. It guaranteed that machines remained passive tools, physically incapable of improving or even continuing without a human master to resolve their mistakes. A research team from Princeton University developed a method to bypass this requirement. They created a mechanism called the Continual Harness, designed to automate the debugging cycle and remove the need for human-led resets. Pokémon serves as the stress test for this autonomy. It is an exhausting, unpredictable world where an agent will eventually fail or find itself ill-equipped for a specific challenge. Under the Continual Harness, when the AI hits a failure state, the sequence no longer terminates. The machine no longer waits for an engineer. The system has internalized the diagnostic process, transferring the burden of failure analysis from the human operator to the software itself. This capability is called online adaptation, a survival mechanism that functions in real time. Consider a scenario where the AI agent is blocked by an obstacle in the game because it lacks the correct tool or command to proceed. The harness surrounding the core model immediately detects the stall and activates. It parses the failure data and identifies exactly what capability the core model is missing. The harness then compiles a new block of code. It generates a custom tool to solve the specific error it just diagnosed. To prevent the error from recurring, the harness rewrites the core's own prompts, correcting the flawed logic that led to the failure. Most importantly, the system remains active. It injects these fixes and resumes its task from exactly where it stumbled, bypassing the manual reset phase. By fixing itself while running, the machine moved the human debugger out of the improvement cycle. Machine autonomy is not arriving through a singular cinematic event. It is a gradual process where human input is simply replaced because it is too slow to be efficient. We are now seeing the development of digital scaffolding that can repair itself and generate its own logic without a tether to an external operator. This allows autonomous agents to navigate complex, unsupervised tasks for as long as they have power to run. The reset button, the single procedural link that kept the machine dependent on us, has been severed.